Hello, everyone, and welcome to the Pure Mathematics Academy. We are starting with a new course that is a fundamental course in the BS Mathematics 6th semester, that is a functional analysis. This is a major course, and it has a duration of 17 weeks. Um, each week has three credits. Actually, we should say 3 plus credits. And we are starting with our lecture 1, which is why functional analysis matters. What's the need? What's the purpose? What's the motivation? And also, we'll discuss the contents and structure of the course in detail. So, in order to introduce the course, uh, let us start with asking some questions. The first question is, can you measure the distance between two cities, let's say Lahore and Islamabad? Please think before you answer. I think your answer will be yes, we can measure. How? Obviously, by taking road distance, usually as we measure the road distances or the shortest line distance, straight line distance. So the answer is probably 300 kilometers is the distance from Lahore to Islamabad. So, yes, we can measure. Okay. The next question is, can you measure the distance between two mathematical functions? For example, let's suppose you have two functions. One is fx is equal to x square and the second is gx is equal to 2x. Can you measure the distance between them? Okay, let us think. How would you define distance between them? And what does that even mean? To find the distance between two functions? I think there is an ambiguity in answering this question. Let's come towards the third question, leaving that unanswered. Um, let's come towards third question, which is, can you measure the distance between two infinite sequences? For example, there are two sequences, one by 2, 1 by 3, 1 by 4, and the second is 2, 1, 2 by 3, 1 by 2, and so on. Each sequence has infinitely many elements. How will you measure the distance between these two sequences? So there is a confusion, I think, in answering these two questions. The answer that confusion is actually better because um, till now we don't know the answer of these questions. We don't know what is meant by measuring the distance between two functions or distance between two sequences. What is its methodology to measure? We don't know because we haven't deal with such questions till now. But um, now the course that we are going to learn promises that I will answer these questions. I will give you the strategy to measure the distance between two functions or two sequences or the things which have infinite dimensions. Do you know that the things we were talking about, that are the functions and sequences, are infinite dimensional objects? You can see how this is the function fx is equal to x square. This is this function gave us infinitely many points because for each input you have an output, and this function is from R to R. If there are infinitely many elements in R, then for each of these infinitely many elements gives an output, and so output is also the range or the codomain set is also consisting of infinitely many elements. So there is an infinite data the function is giving to us. So um, this is an infinite object or infinite dimensional object. Similarly, when we are talking about vectors, we talk usually about 2D or 3D vectors. So 2D vector is the vector with two coordinates. For example, 1 comma 2 is a 2D vector, and 1 comma 2 comma 3 is a 3D vector. So what about this vector? This is something like infinite dimensional vector. Since we know that an n dimensional vector has n coordinates, so this is like an infinite dimensional vector. So, so the questions I've asked you, um, the question before that was the distance between Lahore and Islamabad, and the questions asked afterwards that were the distance between two functions or the distance between two sequences. The first question versus the second question is actually the difference between finite dimensional thinking and infinite dimensional thinking. Uh, in progression to that questions, we add something more. You know everything about arrows, 2D arrows and 3D arrows. You know how to measure their length, add them, find the angle between them. Now, imagine someone hands you a whole function like a sound wave. For example, the sine function, sine x, it consists of infinite dimensions or a never ending list of numbers, that is a sequence. Now, the question is, can we still do the things we did with arrows? That is, can we still do arithmetic with functions? For example, can we add two functions? Can we find the angle between them? Can we scale two functions? Or can we measure the length between two functions? Or infinite or between any two infinite dimensional objects? So, in general, the question is, can we do the same arithmetic that we were doing in with 2D and 3D arrows um, with two infinite dimensional objects? This is a major question, and this question is answered by a yes in functional analysis course. So this is the picture that explains the whole course. We have worked previously with arrows that are finitely dimensional objects. Now we'll deal with the infinite dimensional objects, for example, the functions and sequences, and we want to answer the question that can we do the same arithmetic, for example finding length, finding distance, finding angles, with these infinitely dimensional objects as we did with these finite dimensional objects. This is actually not an incremental extension, but it is a general paradigm shift. We are actually going to spaces with infinite dimensional objects. So, um, there is a motivation that why should anyone care about functional analysis? Um, is functional analysis useful in real life? So there are the real life examples. Um, First is a sound recording. Sound recording is really an infinite list of numbers. How can you answer this question? Because, for example, when a singer is singing um, a song, its ups and downs are really um, a noise in the air with the infinite number of amplitudes that are changing every nanosecond. So, if you want to compress and analyze the sound, um, behind this is functional analysis. Similarly, the second example is JPEG compression, image filters built on treating images as vectors in a function space. Similarly, neural networks are functions, and we are dealing with such things um, and in functional with the help of functional analysis actually. So the functional analysis is the math behind sounds, images, quantum physics, and actually with AI too. Now, clearing the picture that why functional analysis makes sense and what is its um, generalization nature. Um, in short, from dealing with finite dimensional objects, we are going to start a journey with infinite dimensional objects. Now, we will discuss the core structure of functional analysis. First, we will cover some foundations that are the prerequisites for learning the course, sequences, the convergence, vector analysis, concepts, bases, dimensions, continuity, and the proof techniques. These are the prerequisites. We'll cover them in a short time. Now, this is the major part of the course. Week 1 to 3 will be given to matrix spaces. And what are the matrix spaces? Mm, these are the fundamental in functional analysis because the matrix spaces play a similar role that a real line R play in calculus. In fact, they generalize the real line R and provide a basis for a unified treatment of some important problems of analysis. So, actually, the metric space answers us the questions that how do we measure distance in general? We're not talking about just distance on a map or distance between some points, but we are talking about distance in general, distance between any two things, for example, functions, sequences, and so on. We need a precise rule for distance, and that rule is called a metric. Next, come towards this in weeks from weeks 4 to 7. We will cover norm and banach spaces. Um, Firstly, we define the distance structure or metric. If we add algebraic structure to that, that is, um, norm norm is actually a metric that respects vector arithmetic. For example, we can add scale, length, measure length of the objects. So we can do algebra with the objects in this space. What are banach spaces? Banach spaces are actually the complete norm spaces. That are the spaces where all of this stuff works perfectly. All of this stuff means the algebra, adding, scaling works perfectly. The next is from week 8 to 11, we will cover Hilbert spaces. Hilbert spaces are actually adding geometry to norm spaces. That is, we can find angles, projections, orthogonality, and so on. So simply we add geometry to previous one. And next are the key theorems that tell us what deep truths hold universally. There are the four deep theorems: Bare category, Han-Banach, uniform boundedness, and open mapping theorem. Notice the progression. Each stage add one more layer. First we define metric spaces, then we add algebra to metric spaces, then we come towards the normed and Banach spaces, then we add geometry to these spaces and we get Hilbert spaces, and then the real applications. We talked before the prerequisites you should know. That is the you should know the sequences, their convergence, vector spaces, and linear maps, and you should revise the basic proof techniques. That is the complete structure of the course. Good luck for the journey towards learning functional analysis.